A basketball coach has 20 players available. Out of them, he needs to choose 5 for the starting lineup and 7 who will be sitting on the bench. In how many ways can the coach choose these 5 plus 7 players? It is certainly a huge number, but what exactly is it? In this lecture, we will learn how to answer questions of this kind. More abstractly, we will develop methods for counting the number of elements of a given set, which is described in some implicit way. Now, why do we care? The reason is that in many models, the calculation of probabilities reduces to counting the number of elements of various sets. Suppose that we have a probability model in which the sample space, omega, is finite and consists of n equally likely elements. So each element has probability 1 over n. Suppose now that we are interested in the probability of a certain set A which has k elements. Since each one of the elements of A has probability 1 over n, and since A has k distinct elements, then, by the additivity axiom, the probability of A is equal to k times 1 over n. Therefore, to find the probability of A, all we have to do is to count the number of elements of omega and the number of elements of A, and so determine the numbers k and n. Of course, if a set is described explicitly through a list of its elements, then counting is trivial. But when a set is given through some abstract description, as in our basketball team example, counting can be a challenge. In this lecture, we will start with a powerful tool, the basic counting principle, which allows us to break a counting problem into a sequence of simpler counting problems. We will then count permutations, subsets, combinations, and partitions. We will see shortly what all of these terms mean. In the process, we will solve a number of example problems, and we will also derive the formula for the binomial probabilities, the probabilities that describe the number of heads in a sequence of independent coin tosses. So, let us get started. In this segment, we introduce a simple but powerful tool, the basic counting principle, which we will be using over and over to deal with counting problems. Let me describe the idea through a simple example. You wake up in the morning and you find that you have in your closet 4 shirts, 3 ties, and 2 jackets. In how many different ways can you get dressed today? To answer this question, let us think of the process of getting dressed as consisting of 3 steps, 3 stages. You first choose a shirt, let's say this one, and you have 4 choices of shirts. But each shirt can be used together with one of the 3 available ties to make 3 different shirt-tie combinations. But since we had 4 choices for the shirt, this means that we have 4 times 3 equals 12 shirt-tie combinations. Finally, you choose a jacket. Each shirt-tie combination can go together with either jacket. And so the fact that you have 2 jackets available doubles the number of options that you have, leading to 24 different options overall. So 24 is the answer to this simple problem. And how did the number 24 come about? Well, 24 is the same as the number of options you had in the first stage times the number of options you had in the second stage times the number of options you had in the third stage. Let us generalize. Suppose we want to construct some kind of object, and we're going to construct it through a sequential process, through a sequence of r different stages. In the example that we just considered, the number of stages was equal to 3. At each one of the stages, you have a number of options that are available. So in our example, at the first stage, we had 4 options. At the second stage, we had 3 options. And at the last stage, we had 2 options. What is important is that when you reach stage I,
No matter what you chose, no matter what you did at the previous stages, the number of options that you will have available at stage I is going to be that fixed number n sub I. So what is the answer? How many different objects can you construct this way? Well, just generalizing from what we did in our specific example, the answer is the product of the number of choices or options that you had at each stage. This is the counting principle. It's a very simple idea, but it is powerful. It will allow us to solve fairly complicated counting problems. However, before we go into more complicated problems, let us first deal with a few relatively easy examples. In our first example, let us consider license plates that consist of 2 letters followed by 3 digits. The question is, how many different license plates are there? We think of the process of constructing a license plate as a sequential process. At the first stage, we choose a letter and we have 26 choices for the first letter. Then we need to choose the second letter and we have 26 choices for that one. Then we choose the first digit, we have 10 choices for it. We choose the second digit, for which we have 10 choices, and finally we choose the last digit, for which we also have 10 choices. So if you multiply these numbers, you can find the number of different license plates that you can make with 2 letters followed by 3 digits. Now let us change the problem a little bit and require that no letter and no digit can be used more than once. So let us think of the process of a process by which we could construct license plates of this kind. In the first stage, we choose the first letter that goes to the license plate, and we have 26 choices. Now let us go into a second stage where we choose the second letter. Because we used one letter in the first stage, this means that there's only 25 available letters that can be used. We only have 25 choices at the second stage. Now let us start dealing with the digits. We choose the first digit and we have 10 choices for it. However, when we go and choose the next digit, we will only have 9 choices because one of the digits has already been used. At this point, 2 digits have been used, which means that at the last stage we have only 8 digits to choose from. So by multiplying these numbers, we can find out the answer to this question, the number of license plates, if repetition is prohibited. Let us now consider a different example. Suppose that we start with a set that consists of n elements. What we want to do is to take these n elements and order them. A terminology that's often used here is that we want to form a permutation of these n elements. One way of visualizing permutations is to say that we're going to take these elements of the set, which are unordered, and we're going to place them in a sequence of slots. So we create n slots, and we want to put each one of these elements into one of these slots. How do we go about it? We think of putting the elements into slots, one slot at a time. We first consider the first slot. We pick one of the elements and put it there. How many choices do we have at this stage? We have n choices because we can pick any of the available elements and place it in that slot. Next, we pick another element and put it inside the second slot. How many choices do we have at this step? Well, we have already used one of the available elements, which means that there's n minus 1 elements to choose from at the next stage. At this point, we have used 2 of the elements. There's n minus 2 that are left. We pick one of them and put it in the third slot, and we have n minus 2 choices at this point. We continue this way, we keep going on. At some point we have placed n minus 1 of the elements into slots. There's only one element left, and that element necessarily will get into the last slot. There are no choices to be made at this point. So the overall number of ways that we can carry out this process, put the elements into the n slots, by the counting principle is going to be the product of the number of choices that we had at each one of the stages. So it's the product of the numbers n, n minus 1, n minus 2, all the way down to 1. And this product we denoted as a shorthand this way, which we read as n factorial. N factorial is the product of all integers from 1 all the way up to n, and in particular the number of permutations of n elements is equal to n factorial. Let us now consider another example. We start again with a general set which consists of n elements, and we're interested in constructing a subset of that set. In how many different ways can we do that? How many different subsets are there? Let us think of a sequential process through which we can choose the subset. The sequential process proceeds by considering each one of the elements of our set one at a time. We first consider the first element, and here we have two choices. Do we put it inside the set or not? So two choices for the first element. Then we consider the second element. Again, we have two choices. Do we put it in the subset or not? We continue this way until we consider all the elements. There's n of them. And the overall number of choices that we have is the product of 2 times 2 times 2 n times, which is 2 to the power n. At this point, we can also do a sanity check to make sure that our answer is correct. Let us consider the simple and special case where n is equal to 1, which means we're starting with this set with one element, and we want to find the number of subsets that it has. According to the answer that we derived, this should have 2 to the first, that is, two subsets. Which ones are they? One subset of this set is the set itself, and the other subset is the empty set. So we do have indeed two subsets out of that set, which agrees with the answer that we found. Notice that when we count subsets of a given set, we count both the set itself, the whole set, and we also count the empty set. All of these are subsets of our set. At this point, we can now pause and you can try to answer some simple questions of the same kind as the ones that we just practiced. We will now use counting to solve a simple probabilistic problem. We have in our hands an ordinary six-sided die which we are going to roll 6 times. So this is our probabilistic experiment, and we're interested in the probability of a certain event. The event that the 6 rolls result in different numbers. So let us give a name to that event and call it event A. So we wish to calculate the probability of this event. But before we can even get started answering this question, we need a probabilistic model. We need to make some assumptions. And the assumption that we're going to make is that all outcomes of this experiment are equally likely. This is going to place us within a discrete uniform probabilistic model so that we can calculate probabilities by counting. In particular, as we discussed earlier in this lecture, the probability of an event A is going to be the number of elements of the set A, the number of outcomes that make event A occur, divided by the total number of possible outcomes, which is the number of elements in our sample space. So let us start with the denominator and let us look at the typical outcomes of this experiment. A typical outcome is something like this sequence: 2, 3, 4, 3, 6, 2. That's one possible outcome. How many outcomes of this kind are there? Well, we have 6 choices for the result of the first roll, 6 choices for the result of the second roll, and so on. And since we have a total of 6 rolls, this means that there is a total of 6 to the 6th power possible outcomes, according to the counting principle. And by the way, since we have so many possible outcomes and we assume that they're equally likely, the probability of each one of them would be 1 over 6 to the 6th. Incidentally, that's the same number, the same answer you would get if you were to assume, instead of assuming directly that all outcomes are equally likely, to just assume that the different rolls are rolls of a fair six-sided die, so the probability of getting a 2 is 1/6, and also that the different rolls are independent of each other. So in that case, the probability, let's say, of this particular sequence would be the probability of obtaining a 2, which is 1/6, times the probability that we get a 3 at the next roll, which is 1/6, times 1/6, times 1/6, and so on, and we get the same answer, 1 over 6 to the 6. So we see that this assumption of all outcomes being equally likely has an alternative interpretation in terms of having a fair die, which is rolled independently 6 times. Now let us look at the event of interest A. What is a typical element of A? A typical element of A is a sequence of 6 rolls in which no number gets repeated. So, for example, it could be a roll like a sequence of results of this kind, where each number appears just once. So all the numbers appear exactly once in this sequence. So what we need here is basically to have a permutation of the numbers 1 up to 6. So these 6 numbers have to appear in an arbitrary order. In how many ways can we order 6 elements? This is the number of permutations of a set of 6 elements, and as we discussed earlier, this is equal to 6 factorial. So we have now counted the number of outcomes that make event A happen, which is 6 factorial, and by calculating this ratio, we have obtained the probability of the desired event. You can now pause and try to solve a problem of a similar kind. Let us now study a very important counting problem, the problem of counting combinations. What is a combination? We start with a set of n elements, and we're also given a non-negative integer k, and we want to construct or to choose a subset of the original set that has exactly k elements. In different language, we want to pick a combination of k elements of the original set. In how many ways can this be done? Let us introduce some notation. We use this notation here, which we read as n choose k, to denote exactly the quantity that we want to calculate, namely the number of subsets of a given n element set, where we only count those subsets that have exactly k elements. How are we going to calculate this quantity? Instead of proceeding directly, we're going to consider a somewhat different counting problem, which we're going to approach in 2 different ways, get 2 different answers, compare those answers, and by comparing them, we are going to get an equation which is going to give us, in the end, the desired number. The alternative problem that we're going to use is the following. We start, as before, with our given set that consists of n elements, but instead of picking a subset, what what we want to do is to construct a list, an ordered sequence that consists of k distinct elements taken out of the original set. So we think of having k different slots, and we want to fill each one of those slots with one of the elements of the original set. In how many ways can this be done? Well, we want to use the counting principle, so we want to decompose this problem into stages. So what we can do is to choose each one of the k items that go into this list one at a time. We first choose an item that goes to the first position, to the first slot. Having used one of the items in that set, we're left with n-1 choices for the item that can go into the second slot. And we continue similarly. When we're ready to fill the last slot, we have already used k-1 of the items, which means that the number of choices that we're going to have at that stage is n-k plus 1. At this point, it's also useful to simplify that expression a bit. We observe that this is the same as n factorial divided by n minus k factorial. Why is this the case? You can verify that this is correct by moving the denominator to the other side, and when you do that, you realize that you have the product of all terms from n down to n minus k plus 1, and then you have the product of n minus k going all the way down to 1, and that's exactly the product which is the same as n factorial. It's the product of all integers from n all the way down to 1. So this was the first method of constructing the list that we wanted. How about the second method? What we can do is to first choose k items out of the original set, and then take those k items and order them in a sequence to obtain an ordered list. So we construct our ordered list in two stages. In the first stage, how many choices we have? That's the number of subsets with k elements out of the original set. This number, we don't know what it is, that's what we're trying to calculate, but we have a symbol for it. It's n choose k. How about the second stage? We have k elements and we want to arrange them in a sequence. That is, we want to form a permutation of those k elements. This is a problem that we have already studied, and we know that the answer is k factorial. According to the counting principle, the number of ways that this two-stage construction can be made is equal to the product of the number of ways, number of options that we have at the first stage times the number of options that we have at the second stage. So this is one answer for the number of possible ordered sequences. This is another answer. Of course, both of them are correct, and therefore they have to be equal. And by using that equality, we can now find a formula for this coefficient n choose k simply by taking this k factorial factor and sending it to the denominator of that expression. So by equating this expression with that expression here, we find the final answer, which is that the number of choices n choose k is equal to this expression here. Now this expression is valid only for numbers that make sense, so n can be any integer, any non-negative integer, and k, the only k's that make sense would be k's from 0, 1 up to n. You may be wondering about some of the extreme cases of that formula. What does it mean for n to be 0 or for k equal to 0? So let us consider now some of these extreme cases and make a sanity check about this formula. So this is the formula that we have and that we want to check. The first case to consider is the extreme case of n choose n. What does that correspond to? Out of a set with n elements, we want to choose a subset that has n elements. There's not much of a choice here. We just have to take all of the elements of the original set and put them in the subset. So the subset is the same as the set itself. So we only have one choice here. That should be the answer. Let's check it with the formula. The formula gives us n factorial divided by n factorial, and then since k is equal to n, here we get 0 factorial. Is this correct? Well, it becomes correct as long as we adopt the convention that 0 factorial is equal to 1. We're going to adopt this convention and keep it throughout this course. Let us look at another extreme case now. The coefficient n choose 0. This time let us start from the formula. The formula tells us that this should be n factorial divided by 0 factorial and divided by n factorial, since the number k is equal to 0. Using the convention that we have, this is equal to 1, so this is again equal to 1. Is it the correct answer? How many subsets of the given set are there that have exactly 0 elements? Well, there's only one subset that has exactly 0 elements, and this is the empty set. So this explains this particular answer and shows that it is meaningful and that it makes sense. Now let us use our understanding of those coefficients to solve a somewhat harder problem. Suppose that for some reason you want to calculate this sum. What is it going to be? One way of approaching this problem is to use the formula for these coefficients, do a lot of algebra, and if you're really patient and careful, eventually you should be able to get the right answer. But this is very painful. Let us think whether there's a clever way, a shortcut of obtaining this answer. Let us try to think what this sum is all about. This sum includes this term, which is the number of zero-element subsets. This number, which is the number of subsets that have one element. And we keep going all the way to the number of subsets that have exactly n elements. So we're counting 0-element subsets, 1-element subsets, all the way up to n. So what we're counting really is the number of all subsets of our given set. But this is a number that we know what it is. The number of subsets of a given set with n elements is 2 to the n. So by thinking carefully and interpreting the terms in this sum, we were able to solve this problem very fast, something that would be extremely tedious if we had tried to do it algebraically. For some practice with this idea, why don't you pause at this point and try to solve a problem of a similar nature. The coefficients n choose k that we calculated in the previous segment are known as the binomial coefficients. They are intimately related to certain probabilities associated with coin tossing models, the so-called binomial probabilities. This is going to be our subject. We consider a coin which we toss n times in a row independently. For each one of the tosses of this coin, we assume that there is a certain probability p that the result is heads, which of course implies that the probability of obtaining tails in any particular toss is going to be 1 minus p. The question we want to address is the following. We want to calculate the probability that in those n independent coin tosses, we are going to observe exactly k heads. Let us start working our way towards the solution to this problem by looking first at a simple setting and then move on. So let us answer this simple question. What is the probability that we observe this particular sequence? Of course, here we take n equal to 6 and we wish to calculate this probability. Now, because we have assumed that the coin tosses are independent, we can multiply probabilities. So the probability of this sequence is equal to the probability that the first toss is heads times the probability that the second toss is tails, which is 1 minus p, times the probability that the third toss is tails, which is 1 minus p, times the probability of heads, times the probability of heads, times the probability of heads, and by collecting terms, this is p to the fourth times 1 minus p to the second power. More generally, if I give you a particular sequence of heads and tails, as in this example, and I ask you what is the probability that this particular sequence is observed, then by generalizing from this answer or from the derivation of this answer, you see that you're going to get p to the power number of heads. And the reason is that each time that there is a head showing up in this sequence, there is a corresponding factor of p in this numerical answer. And then there are factors associated with tails. Each tail contributes a factor of 1 minus p. And so we're going to have here 1 minus p to a power equal to the number of tails. Now, if I ask you about the probability of a particular sequence, and that particular sequence happens to have exactly k heads, what is the probability of that sequence? Well, we already calculated what it is. It's the previous answer, except that we use the symbol k instead of just writing out explicitly number of heads. And the number of tails is the number of tosses minus how many tosses resulted in heads. Now we're ready to consider the actual problem that we want to solve, which is to calculate the probability of k heads. The event of obtaining k heads can happen in many different ways. Any particular k head sequence makes that event to occur. Any particular k head sequence has a probability equal to this expression. The overall probability of k heads is going to be the probability of any particular k head sequence times the number of k head sequences that we have. Now, the reason why we can carry out this argument is the fact that any k-head sequence has the same probability. Otherwise, we wouldn't be able to write down an answer which is just the product of two terms. But because every k-head sequence has the same probability, to find the overall probability, we take the probability of each one of them and multiply it with the number of how many of these we have. So to make further progress now, we need to calculate the number of possible k-head sequences. How many are there? Well, specifying a k-head sequence is the same as the following. You think of having n time slots. These time slots correspond to the different tosses of your coin. And to specify a k-head sequence, you need to tell me which ones of these slots happen to contain a head. You need to tell me k of those slots. So, in other words, what you're doing is you're specifying a subset of the set of these n slots, a subset that has k elements. You need to choose k of the slots out of the n and tell me that those k slots have heads. That's the way of specifying a particular k-head sequence. So, what's the number of k-head sequences? Well, it's the same as the number of ways that you can choose k slots out of the n slots, which is our binomial coefficient, and choose k. Therefore, the answer to our problem is this expression here times n choose k, which is shown up here. At this point, we can pause and consider a simple question to check your understanding of the binomial probabilities. Let us now put to use our understanding of the coin tossing model and the associated binomial probabilities. We will solve the following problem. We have a coin which is tossed 10 times, and we are told that exactly 3 out of the 10 tosses resulted in heads. Given this information, we would like to calculate the probability that the first 2 tosses were heads. This is a question of calculating a conditional probability of one event given another. The conditional probability of event A, namely that the first 2 tosses were heads, given that another event B has occurred, namely that we had exactly 3 heads out of the 10 tosses. However, before we can start working towards the solution to this problem, we need to specify a probability model that we will be working with. We need to be explicit about our assumptions. To this effect, let us introduce the following assumptions. We will assume that the different coin tosses are independent in the statistical sense. In addition, we will assume that each coin toss has a fixed probability P, the same for each toss, that a particular toss results in heads. These are the exact same assumptions that we made earlier when we derived the binomial probabilities, and in particular we have the following formula, that if we have n tosses, the probability that we obtain exactly k heads is given by this expression. So now we have a model in place and also the tools that we can use to analyze this particular model. Let us start working towards a solution. Actually, we will develop 2 different solutions and compare them at the end. The first approach, which is the safest one, is the following. Since we want to calculate a conditional probability, let us just start with the definition of conditional probabilities. The conditional probability of an event given another event is the probability that both events happen divided by the probability of the conditioning event. Now let us specialize to the particular example that we're trying to solve. So in the numerator, we're talking about the probability that event A happens and event B happens. What does that mean? This means that event A happens, that is, the first 2 tosses resulted in heads, which I'm going to denote symbolically this way. But in addition to that, event B happens, and event B requires that there is a total of 3 heads, which means that we had one more head in the remaining tosses. So we have one head in tosses 3 all the way to 10. As for the denominator, let's keep it the way it is for now. So let's continue with the numerator. We're talking about the probability of 2 events happening, that the first 2 tosses were heads, and that in tosses 3 up to 10 we had exactly one head. Here comes the independence assumption. Because the different tosses are independent, whatever happens in the first 2 tosses is independent from whatever happened in tosses 3 up to 10. So the probability of these 2 events happening is the product of their individual probabilities. So we first have the probability that the first 2 tosses were heads, which is p squared, and we need to multiply it with the probability that there was exactly one head in the tosses numbered from 3 up to 10. These are 8 tosses. The probability of one head in 8 tosses is given by the binomial formula with k equal to 1 and n equal to 8. So this expression, this part, becomes 8 choose 1 p to the first power times 1 minus p to the 7th power. So this is the numerator. The denominator is easier to find. This is the probability that we had 3 heads in 10 tosses. So we just use this formula. The probability of 3 heads is given by 10 tosses, choose 3, p to the 3rd, times 1 minus p to the 7th power. And here we notice that terms in the numerator and denominator cancel out, and we obtain 8, choose 1, divided by 10, choose 3. And to simplify things just a little more, what is 8, choose 1? This is the number of ways that we can choose one item out of 8 items, and this is just 8. We can choose any one of those items, and there's 10 of them. And let's leave the denominator the way it is. So this is the answer to the question that we had. And now let us work towards developing a second approach towards this particular answer. In our second approach, we start first by looking at the sample space and understanding what conditioning is all about. In our model, we have a sample space. As usual, we can denote it by omega, and this sample space contains a bunch of possible outcomes. A typical outcome is going to be a sequence of length 10. It's a sequence of heads or tails, and it's a sequence that has length 10. We want to calculate conditional probabilities, and this places us in a conditional universe. We have the conditioning event B, which is some set, and conditional probabilities are probabilities defined inside this set B, and define the probabilities, the conditional probabilities of the different outcomes. What are the elements of the set B? A typical element of the set B is a sequence which is again of length 10, but has exactly 3 heads. So these are the 3-head sequences. Now, since we're conditioning on event B, we can just work with conditional probabilities. So let us find the conditional probability law. Recall that any 3-head sequence has the same probability of occurring in the original unconditional probability model. Namely, as we discussed earlier, any particular 3-head sequence has a probability equal to this expression. So 3-head sequences are all equally likely. This means that the unconditional probabilities of all the elements of B are the same. When we construct conditional probabilities given an event B, what happens is that the ratio or the relative proportions of the probabilities remain the same. So conditional probabilities are proportional to unconditional probabilities. These elements of B were equally likely in the original model, therefore they remain equally likely in the conditional model as well. What this means is that the conditional probability law on the set B is uniform. Given that B occurred, all the possible outcomes now have the same probability. Since we have a uniform probability law, this means that we can now answer probability questions by just counting. We're interested in the probability of a certain event A, given that B occurred. Now, given that B occurred, this part of A cannot happen, so we're interested in the probability of outcomes that belong in this shaded region, those outcomes that belong within the set B. To find the probability of this shaded region occurring, we just need to count how many outcomes belong to the shaded region and divide them by the number of outcomes that belong to the set B. That is, we work inside this conditional universe. All the elements in this conditional universe are equally likely, and therefore we calculate probabilities by counting. So the desired probability is going to be the number of elements in the shaded region, which is the intersection of A with B, divided by the number of elements that belong to the set B. How many elements are there in the intersection of A and B? These are the outcomes or sequences of length 10 in which the first two tosses were heads, no choice here, and there is one more head. That additional head can appear in 1 out of 8 possible places, so there's 8 possible sequences that have the desired property. How many elements are there in the set B? How many 3-head sequences are there? Well, the number of 3-head sequences is the same as the number of ways that we can choose three elements out of set of cardinality 10, and this is 10 choose 3, as we also discussed earlier. So this is the same answer as we derived before with our first approach. So both approaches, of course, give the same solution. This second approach is a little easier because we never had to involve any p's in our calculation. We got to the answer directly. The reason that this approach worked was that the conditional universe, the event B, had a uniform probability law on it. We now come to our last major class of counting problems. We will count the number of ways that a given set can be partitioned into pieces of given sizes. We start with a set that consists of n different elements. And we have r persons. We want to give n1 items to the first person, give n2 items to the second person, and so on. And finally, we want to give n sub r items to the rth person. These numbers n1, n2 up to nr are given to us, how many items each person should get. And these numbers must add to n so that every item in the original set is given to some person. We want to count the number of ways that this can be done. This is the number of ways that we can partition a given set into subsets of prescribed sizes. Let's use C to denote the number of ways that this can be done. We want to calculate this number C. Instead of calculating it directly, we're going to use the same trick that we employed when we counted combinations and derived the binomial coefficient. That is, we're going to consider a much simpler counting problem, the problem of ordering n items, taking the n items in our original set and putting them in an ordered list. Of course, we know in how many ways this can be done. Ordering n items can be done in n factorial ways. This is the count of the number of permutations of n items. But now let us think of a different way of ordering the n items, an indirect way. It proceeds according to the following stages. We start with the n items and we first distribute them to the different persons. Having done that, then we ask person 1 to take their items, order them, and put them in the first n1 slots of our list. Then person 2 takes their items and puts them in the next n2 slots in our list. We continue this way, and finally the last person takes the items that they possess and put them in the last n sub r slots in this list. In how many ways can this process be carried out? We have C choices on how to partition the given set into subsets. Then person 1 has n1 factorial choices on how to order the n1 items that that person possesses. Person 2 has n2 factorial choices for how to order the n2 items that it possesses, and so on until the last person who has nr factorial choices for ordering their elements. This multi-stage process results in an ordered list of the n items. This is the number of ways this multi-stage process can be carried out. On the other hand, we know that the number of possible orderings of the items is n factorial, so we have this equality. We can solve this for C, and we find the answer that the number of ways that the n items can be partitioned into subsets of the given sizes is n factorial divided by the product of the factorials of the different ni's. This particular expression is called the multinomial coefficient, and it generalizes the binomial coefficient. The binomial coefficient was referring to the case where we essentially split our set into one subset with k elements, and then the second subset gets the remaining elements. So the special case where r is equal to 2 and n1 is equal to k, n2 equals to n minus k, this corresponds to a partition of a set into two subsets, or what is the same, just selecting the first subset and putting everything else in the second subset. And you can check that in this particular case, the expression for the multinomial coefficient agrees with the expression that we had derived for the binomial coefficient. We will now apply our multinomial formula for counting the number of partitions to solve the following probability problem. We have a standard 52 card deck which we deal to 4 persons. Each person gets 13 cards, as for example in bridge. What is the probability that each person gets exactly one ace? Well, before we start, as always, we will need a probability model. We deal the cards fairly, and this is going to be our model, but we still need to interpret our statement. To give this interpretation, let us first think of the outcomes of the experiment. What are the possible outcomes? An outcome of this experiment is a partition of the 52 cards into the 4 persons, so that each person gets exactly 13 cards. Our statement about dealing the cards fairly will be an assumption that all partitions are equally likely. Okay. So, since all partitions, all outcomes of the experiment are equally likely, this means that we can solve a probability question by counting. We need to count the number of elements of our sample space, the number of possible outcomes, and then count the number of outcomes that make the event of interest to occur. Let us start with the number of elements of the sample space. This is the problem that we just dealt with a little while ago. The number of outcomes, the number of partitions of 52 items into 4 persons, where we give 13 cards to person 1, 13 cards to person 2, 13 cards to person 3, and 13 cards to person 4. The number of possible ways of doing this is equal to this multinomial coefficient. So now let us count the number of outcomes that belong to the event of interest, namely the outcomes where each person gets an ace. We think of the process of constructing such an outcome as a multi-stage process, and we count the number of choices that we have at each stage. The process is as follows. We first distribute the 4 aces. We take the ace of spades and give it to one person. In how many ways can we do it? We can do it in 4 ways. Then we take the next ace. The next ace must be given to a different person, and so at that stage we have 3 different choices about whom to give that ace to. Then we consider the next ace. At this point, 2 persons already have aces, so we have 2 available choices for who can get the next ace. And finally, for the last ace, we do not have any choice. We give it to the only remaining person who doesn't yet have an ace. Having distributed the 4 aces, then we need to somehow distribute the remaining 48 cards to the 4 people. But we can do that in any way we want. So all we need to do is to just partition the 48 cards into 4 subsets of given cardinalities. And this can be done by a number of ways, which is the number of such partitions. We have already found what that number is, and it is this particular multinomial coefficient. So the number of ways that we can distribute the cards so that each person gets an ace, according to the counting principle, is going to be the number of ways that we can distribute the aces times the number of ways that we can distribute the remaining cards. The product of this number gives us the count, gives us the cardinality of the event of interest. We also have the cardinality of the sample space, so the desired probability can be found by dividing these two numbers, and the final answer takes this form. Let us now look at the same problem, but in a different way. Probability problems can often be solved in multiple ways, and some can be faster than others. So we want to look for a smarter solution that perhaps will get us in a faster way to the desired answer. We will use the following trick. We will think about a very specific way of dealing the cards, which is the following. We take the 52 cards, the card deck, and stack it so that the 4 aces are at the top, so they are first. And then we deal those cards to the players as follows. We think of each player having 13 slots of his own, and the cards will be placed randomly into the different slots. So we can do this one card at a time, starting from the top. We take the first ace and send it to a random location. Then we will take the second ace, send it to a random location, and so on. What we want to calculate is the probability that the 4 aces will end up in locations or in slots that are associated with different persons. So let us calculate this probability. The first ace can go anywhere, it doesn't matter. For the second ace, it has 51 slots to choose from. It's 51 because we started with 52, but one slot has already been taken by that particular ace. So for the ace of hearts, we have 51 slots that it can go to. And out of those 51, we have 39 of them that belong to people who do not yet have an ace. So this is the probability that the ace of hearts gets placed into a slot that belongs to a person who is different than the person who got the first ace. Now let us consider this ace. What is the probability that this ace will get into a slot which belongs to either this person or that person? It has 26 slots in which this desired event is going to happen, and it's 26 out of the 50 available slots. Finally, let us consider this ace. So having placed that ace and assuming that it got to a different person, what is the probability now that this ace is going to go to this person who doesn't yet have one? The probability of this happening is the number of slots associated with that person, which is equal to 13, divided by the number of slots that this card can choose from, and the number of slots is 52 minus the 3 slots that have already been taken, so it's 49. And so this is the answer to our problem. This expression looks very different from the expression that we derived a little earlier, but you can do the algebra, the arithmetic, simplify the answer, and you will verify that indeed it's exactly the same answer. And in case you're curious, the numerical value turns out to be 0.105. So there's about 10% that when you deal the cards in bridge, each one of the players is going to end up by having exactly one ace. So this was a faster way of getting to the answer to our problem compared to the previous one, but it raises a legitimate question. Is the way that we dealt the cards by putting the aces on top and then dealing them, is that way a fair way of dealing the cards? Is it true that with this way of dealing the cards all partitions are equally likely? It turns out that this is indeed the case, but it does require a bit of thinking. Maybe you can see it intuitively that this is the case, but if not, then it is something that one can prove. It can be proved formally as follows. One first needs to check that all permutations, that is, all possible allocations of cards into slots, are equally likely. And because of this, one can then argue that any possible partition into subsets of 12 is also equally likely. So this is an equivalent way of dealing the cards to the one that we considered earlier, which was that every partition is equally likely. Therefore, we did indeed solve the same problem, and so this is a legitimate alternative way of getting to the answer. And of course, it's reassuring to check that this numerical expression agrees with the numerical expression we had derived earlier. In this segment, we will discuss the multinomial model and the multinomial probabilities, which are a nice generalization of the binomial probabilities. The setting is as follows. We are dealing with balls, and the balls come into different colors. There are possible different colors. We pick a ball at random, and when we do that, there is a certain probability pi that the ball that we picked has the ith color. Now we repeat this process n times independently. Each time we get a ball that has a random color. And we're interested in the following kind of question. Somebody fixes for us certain numbers, n1, n2 up to nr, that add up to n, and asks us what is the probability that when you carry out the experiment you get exactly n1 balls of the first color, exactly n2 balls of the second color, and so on. So the numbers n1, n2, and up to nr are fixed given numbers. For a particular choice of those numbers, we want to calculate this probability. Now, of course, this is a more general model. It doesn't necessarily deal with balls of different colors. For example, we might have an experiment that gives us random numbers, where the numbers range from 1 up to r, and at each time we get a random number with probability pi, we get a number which is equal to I. So we could use this to model die rolls, for example. And there is actually a special case of this problem which should be familiar. Suppose that we have only two colors, and instead of thinking of colors, let us think of the two possibilities as being heads or tails. And we can make the following analogy. Somebody gives us numbers n1 and n2 that add up to n, and we're interested in the probability that we get n1 of the first color and n2 of the second color. Well, we could think of this as a setting in which we're asking for the probability that we obtain k heads and n minus k tails. So the question of what is the probability that we obtain k heads and n minus k tails is of the same kind as what is the probability that we get n1 of the first color and n2 of the second color. Now, if heads have a probability p of occurring and tails has a probability of 1 minus p of occurring, then we would have the following analogy. The probability of obtaining the first color, which correspond to heads, that would be equal to p. The probability of obtaining the second color, which correspond to tails, this would be 1 minus p. Now, the probability of obtaining k heads in those n independent trials, we know what it is. By the binomial probabilities, it is n choose k times p to the k times 1 minus p to the power n minus k. Now we can translate this answer to the multinomial case where we're dealing with colors, and we do these substitutions. So n choose k is n factorial divided by k factorial. In this case, k is the same as n1, so we get an n1 factorial. And then we're going to have here n minus k factorial. But n minus k corresponds to n2, so here we get an n2 factorial. And then p corresponds to p1, and p2 corresponds to 1 minus p. So we get here p1 times p2, and the power n minus k, again by analogy, is n2. So this is the form of the multinomial probabilities for the special case where we're dealing with two colors. Let us now look at the general case. Let us start with an example. To be concrete, suppose that the number of colors is equal to 3, and that we're going to pick n equal to 7 balls. We carry out the experiment and we might obtain an outcome which would be a sequence of this type. So the first ball had the color 1, the second ball had the first color, the third ball had the third color, the fourth ball had the first color, and so on. And suppose that this was the outcome. One way of summarizing what happened in this outcome would be to say that we had 4 ones, we had 2 twos, and we had 1 3. We could say that this is the type of the outcome. It's of type 4 to 1. That is, we obtained 4 of the first color, 2 of the second color, and 1 of the third color. This is one possible outcome. What is the probability of obtaining this particular outcome? The probability of obtaining this particular outcome is, using independence, the probability that we obtain color 1 in the first trial, color 1 in the second trial, color 3 in the third trial, color 1 in the fourth trial, color 2 in the next trial, color 2 in the next trial, color 1 in the last trial. And we put all the factors together and we notice that this is p1 to the fourth, p2 to the second, times p3. It's not a coincidence that the exponents that we have up here are exactly the counts that we had when we specified the type of this particular outcome. Generalizing from this example, we realize that the probability of obtaining a particular sequence of a certain type, that probability is of this form. For each color, we have the probability of that color raised to the power of how many times that particular color appears in a sequence. So any particular sequence of this type has this probability. What we're interested in is to find the total probability of obtaining some sequence of this type. How can we find this probability? Well, we will take the probability of each sequence of this type, which is this much, and it's the same for any particular sequence, and multiply with the number of sequences of this type. So how many sequences are there of a certain type? Let us look back at our example. We had 7 trials, so let us number here the different trials. And when I tell you that a particular sequence was obtained, that's the same as telling you that in this set of trials we had the first color. In this set of trials, the 5th and the 6th trial, we had the second color. And in this trial, the 3rd trial, we had the 3rd color. This is an alternative way of telling you what sequence we obtained. I tell you at which trials we had the first color, at which trials we had the second, at which trials we had the third. But what do we have here? Here we have a partition of the set of numbers from 1 up to 7 into 3 subsets, and the cardinalities of those subsets are the numbers that appear here in the type of the sequence. The conclusion is that a sequence of a certain type is equivalent or can be alternatively specified by giving you a partition of the set of tosses, which is the set from 1 up to n, how many trials we've had, a partition into subsets of certain sizes. So this allows us now to count the number of sequences of a certain type. It's exactly the same as the number of partitions, and we know what this is, and putting everything together, the probability of obtaining a sequence of a certain type is equal to the count of how many sequences do we have of a certain type, which is the same as the number of partitions of a certain type, times the probability of any particular sequence of that type that we're interested in. So this is a formula that generalizes the one that we saw before for the case where we have only 2 colors and which corresponded to the coin tossing setting. And it is a useful model because you can think of many situations in which you have repeated trials, and at each trial you obtain one out of a finite set of possible results. There are different possible results. You repeat those trials independently, and you may be interested in the question of how many results of the first kind, of the second kind, and so on there will be.